Okay, so I'm going to explain where this. I like to give a little bit of flavor of the book every time. So where this deviation bound come from? Why this regime? Okay, why this is a sufficient condition, and it's going to come from a concentration inequality. Okay, because you remember what G is. G is the average. It's empirical Gramian. It is the average of the W of yi, Lk of yi, Aj of yi. Okay, that's the entries. So you can think of G as an average of matrices. So you can think of G as an average, empirical average of a random matrix. These xi are just realization, independent, of a random matrix, which is actually a rank 1 matrix, which is n times n, okay, which is of that form. So it's a random matrix because y is a random, this random variable distributed according to sigma. Okay? And its expectation is the identity, right? Because the expectation is the integral of this with respect to d sigma, so it's the integral of this with respect to 0, so it's the identity. Okay? Because it's an orthonormal basis. Okay? So the question is, can you control the probability that an empirical average of matrix deviates from its true average? Okay, that is a concentration bound for matrix. Who has never seen a concentration bound for scalar random variable? Just as a poll. Everyone knows. Who knows what Hovding inequality is? Or not everyone. What? No, but again, no, well, okay, just no, it's fine. I will just give an idea just to understand. So think of think of x to be a scalar variable, to be simple, and so I'm going to draw realization. And to be simple, let's assume that its expectation is 0. Okay, so I want to understand how it concentrates. So I'm interested in evaluating the probability that 1 over n, sum of the xi from I equal 1 up to n. Xi are IID realization of x. I draw x n time, and I would like to understand to evaluate the probability that this is bigger than t. Okay? Right? So the first thing, I think, okay, you may not know concentration inequality, but each one of you know a little bit, has seen the strong law of large number and the central limit theorem. The central limit theorem tells you that as n goes to infinity, this converges in law to a Gaussian distribution. This looks more and more like a Gaussian distribution, but with variance sigma square over n. Okay, the variance decrease. Okay, so what is expected? What would be expected? Hoped for is something like a constant exponential, let's say a Gaussian tail, take into account this n, so something like minus nt squared times some constant. Yeah? This is what we want to understand if we have some sort of thing like this. Okay, so that's the goal of concentration inequality, to understand in which circumstance you have something like that. You cannot have this for any variable. You need that they are somehow concentrated from the start. So, and Hoeffding's inequality, for example, does this. Hoeffding inequality does this under the assumption that this variable is bounded almost surely. So x is less than some bound n. Okay, so what can we do in that case? What is the strategy? So you see, you will just look at only on one side. You will look at the probability that 1 over n sum of the xi is bigger than t. You can treat less than minus t in the same way. So you want something like that, sum of the xi bigger than nt. Okay? That's what you want to evaluate. And you can actually multiply. This is the same as if you have any number lambda, you can multiply by any number lambda. This is the same thing, right? That doesn't change. And you can also take any monotone increasing function from both sides. We're going to take the exponential. So we say this is like the probability that exponential of a sum of lambda xi, so lambda sum of the xi, is bigger than exponential lambda nt, right? And now what do? We use Markov inequality. Okay, so we bound this probability by exponential minus lambda nt multiplied by the expectation of this variable. Okay? Expectation of the exponential. Okay? Okay. Now this is interesting because the expectation of this sum is a product of the exponential of the sum is a product of the exponential, and these variables are independent. Okay? So you just say that the expectation of a product of independent variable is the product of expectation, right? So you can bound this by, you see, expectation of the exponential of lambda x, because it's always the same variable, but this is to the power n, times exponential minus lambda t, everything is to the power n. And this is what we want to, this is what you want to compute now. Okay? Right? So how do you do that? Let's see. I need more space. Right, now we're going to remember, we have to, so we want to look at the expectation of exponential lambda x. We have, this is what we want to compute. And we're going to remember that x is centered, has zero expectation. And we're going to use just so we're going to look at this, and we're going to extract x. So one way to do that, you see, is a rather simple way is to remark that if you look at exponential z minus z for any number, this is always less than z plus, okay, I'm very generous here, I put z plus exponential z squared. Everyone can prove that. It's very, very easy to prove. Okay? So now you remove this, you use the fact that the expectation of x is 0, and you get that this is less than expectation of exponential lambda square x square, and you remember that x square is bounded by m. That was our assumption, no? So now m is a deterministic thing, so you get exponential lambda square m square. Okay, so if you remember the other factor, you had exponential lambda square m square, exponential minus lambda t, right? And everything was to the power m. Okay, that was our bound for the probability. And now the idea is to choose lambda in order to make this small, right? So we optimize the value of lambda to make this the smallest as possible. So what is the good value of lambda? Let's see. Now we have a quadratic function. We look at where it takes its minimum value. So it's going to be lambda equal t over 2m squared. If we take lambda equal t over 2m squared, what do we get? We get, you see that we get exponential minus t squared divided by 4m squared, and this gets multiplied by m, so mt squared divided by 4m squared. Okay, that's solving, but it's not actually a thing because I was a bit lazy by writing this. You can improve on this. You can put actually a 2 in the numerator instead of this 1 over 4 if you work a little bit harder. All right? So you see how you do that, but what was critical was to have a little bit of information on the random variable. And now we have the same question, but we have matrices. Okay, so I think if you see what I did, where is the trouble with matrices? If I want to do the same with matrices. Do you see where if I would like to proceed exactly the same way, do you see where it's not so easy? The problem is here. The problem is when I look at the exponential of the sum of matrices, it's not going to be in general the product of the exponential. Okay? Otherwise, life would be much easier. But of course, these matrices do not commute in general. So this is why this is one way of thinking why concentration bound for matrices are not going to be as simple to prove as for scalar variable, but there's a very nice literature on this, and there's a good understanding here. So maybe the most there's a very nice survey by Cohen, but he's quite an expert in this, and when I came with this problem, he said, "Oh, you should look at a very, very basic example of such concentration bound." And it's the matrix Chernoff bound. So of course the proof is much more involved than what I wrote. But it's a bit the same idea because you need an almost sure bound on your matrix. Think of very similar to optics. So you assume some bound on the spectrum now, almost surely. And the Chernoff bound tells you that this empirical average deviates from the expectations by delta with a probability less than this. So you have n, the size of the matrix that comes into play. You have this exponential here, and here you have m. You have a constant that depends on delta. So in my case, remember I want delta to be 1/2. This is enough for my purpose. So this constant becomes what I wrote 3 times log of 3 half minus 1. This is a constant that I had in my previous slides. Okay, so that's the bound, what will come in place of the Hövding bound. And now let's see what is this K. What this K is an almost sure bound for the norm of this matrix. This is a rank 1 matrix, you see. This is actually the product of a column vector by its row. Huh? So the spectral matrix of A times A transpose is just the square norm, the square Euclidean norm of A. So what it is exactly the sum of V squared. This is what I call KNW. All right? And we want to control this almost surely, so we have to look at the soup. Otherwise, this is exactly this quantity. Okay? So now that explains you. If KNW satisfies this inequality, if you have this stability condition, this is exactly what you need to kill here this thing, okay, and end up with epsilon in the probability. All right? So, okay, everything comes from there. So you have the explanation of the regime, and as I said, the regime tends to look sharp numerically. Okay, let me give other examples than polynomials, but I want to. If you have local basis, think of piecewise constant function, then in that case, you see, if you have a partition, then you have a clear orthonormal basis by taking the characteristic function and normalize them well. And so if you would like that Kn is minimum, actually, that will hold only for very particular partition. If the partition is actually uniform with respect to rho, if it equidistributes the measure. But for other general partition, that will not happen. So that will mean that you will have a problem with Kn. Okay. Let's look at the trigonometric system is a nice system where everything goes well when rho is a uniform measure, because Lj is now the complex exponential, so it's completely flat. So the Christoffel function Kn is just the sum from 1 up to n of the square of these complex exponential. Each of them is 1. You get n times 1, you get n. So this is a rather good situation. Actually, there is a generalization. Whenever you have a compact Riemannian manifold and you look at the first eigenfunction of the Laplace-Beltrami operator, then you can prove that Kn will be also order n. So, for example, if you think of the spherical harmonics, individually they are not uniformly bounded. This is not like the complex exponential, but when you sum them, when you average, on the average, they are essentially bounded because you have this estimate. Okay, but there are other spaces where things are not so good as we saw, for example, with the Gaussian measure. Okay, this is just an example. For my very first problem, if you remember, I had an acoustic problem where I wanted to sample. And in that case, we find that the unknown function satisfies some Helmholtz equation, but you don't know the boundary condition, and otherwise you would just solve. And the spatial frequency was linked with this considered temporal frequency. That was my very first example of placing microphones. And in that case, it's kind of interesting to use as a space Vn, space generated by particular solution to this equation, plane wave. You just take plane wave with the right eigen frequency, and you have quite a good approximation theory with this space. But of course, you cannot take infinitely many of them, so you need to sample the wave number. Here it's sampled along a circle because you want that the modulus of the wave number is given by this lambda. Okay? And there's a very nice theory about approximating from these spaces that shows that you have quite a good, actually, spectral approximations. Okay, so now we can ask for this space, what is the the inverse Christoffel function? And we could analyze this in a very simple case where when the domain is a disk. We find that it is a little bit the same as for Legendre functions, as for polynomials. If you use the uniform measure over the disk, Kn will scale quadratically. But if you put a little bit of measure on the boundary of the disk, so you just put the uniform measure and you combine with a little bit of measure along the boundary, then you retrieve the linear behavior. Okay, so there is something interesting. You can get something better, and this is actually shown with this error curve. So here, this is the number of this is the number of snapshots. Oh no, this is this is the proportion, and this is the number of planar wave. Yeah, and the idea is this is using a fixed number of microphone, but if you place them uniformly, like here, very quickly the method becomes unstable. So you stabilize the method by putting a little more along the boundary. Okay, that's the error of approximation. So that's what this analysis tells you. And in high dimensional approximation, well, again, we consider these downward closed polynomial spaces. That's we've seen already before. We have all kind of approximation results. That's what we saw. And again, we can try to understand what is a stability regime for least square. Well, if you have the uniform distribution, there is an interesting result that tells you that it's a bit similar as what you have in 1D, that for this space, the inverse Christoffel function has L infinity norm which is going to behave better than n squared, but sometimes like n squared, independently of the downward closed set that you use. All you need is that control its cardinality. So this is rather nice because this is dimension free, doesn't depend on the dimension, but there is still this quadratic scaling which you don't like. If you use the Chebyshev measure, then you improve, but you don't improve to a linear scaling. Okay, and of course, because of what we already saw, we will not be able to handle log normal diffusion if we do this unweighted strategy, because we have the Gaussian measure, and we saw that with the Gaussian measure, this is a very bad idea to use an unweighted strategy. So now we go to, let me go to the weighted strategy. And I want to finish with that. And we will see that this will be the solution to the problem. So remember, we sample according to d sigma, and we have this thing. And we have the stability condition. So KNW is the supremum of W times Kn being the sum of the Lj squared. Okay? And of course, our goal is to make this as small as possible. Okay? And now we have the choice. We can choose d sigma and we can choose W. So how are we going to choose this? Well, this is very simple. We're going to take as a sampling measure something which is described by the product of the original measure rho with the inverse Christoffel function up to this n. So W will be given by this. Let me observe that this is indeed a probability measure, because if you integrate, each term integrates to 1 and the whole thing integrates to 1. So you have defined a probability measure. And with this particular choice, let's look at this. Well, since this is exactly the inverse of this, you see that KNW is constant equal to n. So it has the optimal value. So it's very simple. Okay? So that means that if you are decided to use this measure, then the stability regime becomes optimal at 2 log factor, independently of rho. So you have instance optimality, well, in this probabilistic sense, with an optimal sampling budget. So the message is, give me any space Vn, give me your favorite measure rho, and I'm going to design you a measure which is the right measure to sample. Okay? There is something still which is interesting. You see, rho was a fixed measure. Now we have a measure that changes as we vary the space Vn. This is going to be an issue because we go, if I go from Vn to Vn plus 1, this is not anymore the same measure. So what should I do? How can I recycle if the measure has changed? That's interesting. We have an issue here. And this measure is not as simple as rho. You remember rho was typically the uniform measure or the product of the uniform measure in several dimensions or the product Gaussian measure. That's easy to sample according to rho. It doesn't look as simple to sample according to this optimal measure, especially in high dimension, but we're going to say something about it. So you see, this is again an illustration. Let's go back to this example. So on the left you have the rho has different values. This is, you remember the regime, the stability regime, if you use the rho as a sampling measure. And this is a stability regime if you use sigma as a sampling measure for these different measure rho. So you see that in that case, everything becomes essentially optimal, regardless of the measure rho that you took. That's quite good. I mean, we have solved the problem essentially by taking the right thing. You have the optimal budget. However, completely. I'm impressed by this when I look at this kind of thing. Anyway, so we have this density now, and this density depends on Vn. So typically, in the example I have in mind, rho is a product measure. It's easy to sample. This is not as easy to sample. We need some sampling strategy in practice. Huh? So the most general strategies are iterative method like Monte Carlo Markov chain, and try to approach asymptotically this distribution. But you can do something much simpler in the particular case where the Lj have a nice structure. So remember, typically there would be tensor product, Legendre polynomials, or other things. And so you can use the fact that you have an explicit formula. So you can do, for example, you can work component-wise. That's what we call conditional sampling. We have a multivariate distribution. We first sample according to the marginal, first component, and then conditionally to what we find, we look at the conditional marginal probability. We sample the second condition. Another remark is that this is a mixture. I will come back later to this. So it means you could sample according to a single probability Lj 0, which is now a product measure if these Lj are tensor product, and sample this with probability 1 over n each time, okay? This is a mixture. Okay, so there are ways, but of course, the more rho becomes difficult, the more these Lj are less explicit, the more this gets difficult. Okay. This is just a remark about pseudospectral method, because later I became aware of a work on pseudospectral method. They do not really call this pseudospectral method, they call this Monte Carlo method, by people in information-based complexity, where they actually use exactly the same measure. So recall that pseudospectral method, so this is work by Wozniakowski, Wasilkowski, but recently it has been improved by David Crick. In pseudospectral method, what is the idea? We replace the true coefficient by the one computed by this quadrature, okay? And we would like to understand how well we do compared to the orthogonal projection. So let's compare those two. So in L2 norm, this is just the sum of this square. That's the true coefficient, that's the one computed by quadrature. Okay? Let's look at the expectation of each of these terms. Well, since these are just the empirical average for these, again, the expectation of this is just the variance of this random variable. The variance of this random variable, you see, is bounded by the integral of the square of this. You see that we can swallow one of the w with d sigma to get 0. And now what happens if we sum this thing over j equal 1 up to n? Well, we find again the Christoffel function that is going to cancel out with w if we took the optimal sampling measure. So what in the end we obtain is a very simple expression. We obtain that if we took this optimal sampling, we get that the deviation is u squared times n divided by m. N is the dimension, m is the amount of snapshots. We look at this is not great, okay? Because this is certainly not as good as the best approximation error. So we did a lousy job if we just look at this, okay? But actually, those people are smart. I mean, they just don't do that. They use this as a starting point to something more clever. And the idea is to use a multi-level strategy. So I can summarize as follows their idea. The idea is to say, okay, we're going to have this crude estimate, but for the very coarse space, and now we're going to improve, and the way we improve is the following. So we're going to act geometrically. We are going to raise the dimension. And suppose that we have already constructed an approximation in Vn L-1. Then we draw the snapshots again, new snapshots according to this measure, the new measure for space VNL. So what's important is that the growth of n is in that case, it's not linear. We go from dimension 1 to 2 to 4, etc. But we always take a number of samples which is proportional to NL with a certain theta, which I will explain the role of. Okay, theta is going to be bigger than 1. And now we want to define our new approximation. How are we going to do? We are going to correct, and we apply the pseudospectral method on the residual. Okay? So that's what we do. So what is the payoff to that? The payoff is that now we are improving on the approximation of the previous one, because here we have the residual, so we have to remember what we have. We had expectation of u squared times n divided by n. Now we have nl divided by ml, but now we don't have expectation of u squared, we have expectation of the residual. Okay? And this thing is less than theta minus 1 because of this. Okay? So we have a sort of, we have here the error, and here we have the previous error with a damping factor. Okay? So we recurse, and you see that the damping factor is going to tell us that we are forgetting more and more the error which are allowed, the first terms. So we get this kind of series. And immediately you look at this series, and you find that if En was decreasing like n to the minus s, if you took this theta constant but bigger than 2 to the 2s, then you retrieve the same rate. You retrieve rate optimality. So you don't get instance optimality, but you retrieve rate optimality, and the sampling budget is optimal. So because you see, since you grow geometrically, essentially everything is dominated by the last step. You don't even have the log factor, but you don't have instance optimality. You have rate optimality. There's in the paper I mentioned by Krieg, is actually retrieving instance optimality, but under condition which I don't like too much. He assumed that he knows exactly what En is, which is precisely don't really know. And maybe the defect of this method is that you impose this geometrical growth. As I said, in my adaptive scheme, my idea is that you don't want to go, you want to be a bit more careful, go one by one, and still maintain something. So this is what I will finish with. Return to least square, weighted least square, and try to do this now in an incremental manner. So every time we enrich, let's say we enrich by 1 or by 2, and so the problem is, again, this measure is changing. So can we manage to recycle the previous sample? Okay, there are cases which are interesting. For example, the case of the polynomials on an intervals with a uniform measure or with any Jacobi measure. Then there is a sort of limit to this measure sigma n in terms of what's called the equilibrium measure. But in general, this is not going to happen. Let me give examples. You see, this is for Hermite polynomials. So this is in 1D. Imagine you enrich by adding more and more Hermite polynomials. And this is what the optimal measure looks like. Okay, so it's a product of the Gaussian measure with the sum of the Hermite polynomial square. And you see, it's not at all like the Gaussian measure. It really looks different, and it changes every time you enrich. This is something else. This is a space. In that case, rho is the uniform measure, and the space is generated by wavelets. I'm refining by adding at certain places more wavelets at the fine scale. And this is what the density looks like. And intuitively, it's quite clear what's going to happen. Where you add, where you increase the resolution, this is where you want to sample more. So the density becomes like that. It changes. Okay, so how can you manage this? Very simple. You make the following observation. You realize that if you look at this measure, well, it is actually, you can view it as a combination of the previous measure, sigma n minus 1, a barycentric combination, and an update. Okay? It has this particular mixture structure. Okay? So then the strategy is clear. Suppose that you have built your sample y1, ym, and m depends on n minus 1, based on your previous measure. Then the way we can build a new sample for the next measure sigma n would be the following. We're going to take with probability 1 over n sample according to this d mu n with the new measure. And with probability 1 minus 1 over n, we will recycle the one which are already sampled according to this. And if they are exhausted, we sample again according to this measure. So it's quite simple. What is the payoff of this? The payoff is that the cumulated budget remains optimal. So this is what this theorem tells you. The theorem is that you maintain optimality uniformly for all values of n, and the total number of samples that you have used until stage n remains optimal up to log factor. This is actually what you can see here. Okay, so that's the number of samples you need. This sample itself becomes, this number becomes itself a random number, but you control it. Okay. Yeah, there's another strategy that was later proposed by Giovanni Migliorati, which it's quite nice actually. It's the idea of working completely deterministically. So, well, not deterministically, but working with a deterministic mixture, namely saying we are going to do a number of batch inside the sample, and each of them will be generated according to the update measure. So to a different measure. So, but you fix the size of this batch. You don't play the dice like I do here. And he has interesting results with that. Okay, so I'm essentially done. So the message was that you give me any measure rho, any space Vn in any dimension, you can preserve optimality with non-intrusive method, but all these convergence results are in expectation. I cannot provide you with a deterministic result here. One first step would be to try to have similar convergence result with high probability. Try to prove something for the L infinity norm. I don't have any good result here. And now, of course, the idea is to go for adaptive method using this. So I didn't at all explain the strategies for selecting this index set on an adaptive manner, but we have all kind of strategies for that. And there are interesting things to do. For example, when everything I do works very nicely for these parametric PDs, because your domains are typically tensor product. They have simple geometry. They are high dimensional, but they are at least geometrically simple. If you don't have geometric simplicity, then it becomes a little bit more difficult to compute this optimal measure. Actually, it's an interesting question. I give you a general domain with a very, and you want to do polynomial approximation. What is a good sampling in such a domain? A polygon. Okay. Do you have a very natural strategy? So you could follow this, but it will be more difficult. Okay. And here everything is based on the data. Again, the data are point values. So you could imagine different type of data, different types of sensing system, and to what extent, for what type of, in what setting could I would be interested in extending this kind of theory for more general sensing system and defining some good sampling measure for typically think of a dictionary of linear form equipped with a measure, and you would like to understand how you should pick. Okay, these are references. I gave already all kind of references. So again, maybe those who want to learn more on the first part will be interested in this one, and also on these two papers, and this is a paper that deals with these optimal square methods, these optimal sampling strategies. And I think I'm on time, so I will stop here. Thank you.
Questions? Comments?
Yeah. So in the experiment, in the plot you showed, it actually looked like sampling purely along the boundary performed okay as well.
Ah, yeah, that's interesting about this acoustic problem.
Yeah.
Okay, very good. No.
Okay.
So in fact, what happened? But this is very good. This is when we did this, we were not aware of this idea of weighting. Everything is with the unweighted case. Okay, so that's really purely square. So in fact, indeed, the more you put things on the boundary, the best. In principle, you get something which is going to be better and better for instance optimality. But instance optimality with respect to L2 of rho, where rho is this measure where you put more and more on the boundary. Okay, so here the error is measured everywhere, because this is really what I want in the end. I would like to measure the error everywhere. So you see exactly the problem here. If I put everything on the boundary, okay, I get very good, something which is going to be very good, but for approximating on the boundary.
So it's only the error on the boundary,
which is going to be good. But you see, in that case, the error is not so good for this one. Here, the error is good because you still have a little bit of mass inside to control the error everywhere. Okay? So, you see, this is showing you the defect of this approach, of the non-weighted approach. Because that was our first thing. Let's try to work like hell, think what should be the good measure to make this Christoffel function small, linear, okay? And of course you could find a measure, but in the end this may not be a very good, interesting measure for your purpose, okay? If I can only guarantee that the error will be good on the boundary, what is this, I mean, okay?
So alpha equals to 1 is when we are only measuring on the boundary.
Yeah, alpha 1 is everything on the boundary. Okay. Alpha 0 is completely uniform.
Okay.
And you see the good choice is when you are typically here.
Okay.
So you put quite a bit on the boundary, but you still leave some a bit of uniform inside. Yeah.
Were you able to, I'm guessing problem dependent, right? But
I
were you able to determine, problem dependent, but were you able to determine, for example, like what an optimal alpha would be? Or just like curiously you were able to see, hey, it's good between 0.5 and 0.5?
No, yeah, we don't have a good. No, and as I say, now I wouldn't do it this way. Now I would really go for and actually Gilles Chardon, who did that, he's been following now this other strategy. this is really how you have to do it. No, I was not, that was before we did this, we realized that this is a good way to go with these weights. Yeah. Question?
Again, this, you basically get rate optimality.
Yeah.
In the sampling method, right? If you
Yeah. You get instance optimality for the least square, and for the pseudospectral you get essentially rate optimality, but with this multi-level trick.
You get the rate, you get the instance optimality by controlling the epsilon.
Yeah. So you're right. I mean, you get you have to be honest indeed. You get instance optimality up to this probability of failure, and so you then if you have a rate, then you really manage so that this probability of failure is below your.
So when you want to be adaptive, you would really ideally need a way to evaluate your error in an a posteriori way.
Yeah, I guess so.
With high probabilities. Is that where
yeah.
you need your high probability estimate?
And as I said, this is not as simple as
That's
to
generally
do as
a very open problem, right? It's non-intrusive.
yeah, to have something with
Evaluating
high probability. No, that's
your
that's an
accuracy in a
interesting
posteriori way.
that's an interesting direction, I think. Yeah. Yeah, high probability. It's not as easy as an expectation. We do see in practice. We do see that. It seems to work quite fine.
Okay.
Yeah.
Is it substantially, are there any substantial difficulties in dealing with the noisy case when the samples are?
No, okay, so I didn't do anything indeed. I mean, I could give you a, so I have a similar result in the noisy case, and essentially what you will find if you have what you observe is are these yi zi because u of yi plus eta I, where these are IID, let's say, and the expectation of, they are centered, okay? So expectation of eta is 0, and expectation of eta square is sigma square, right? And the typical result I will find is that under the same stability regime, so KNW less than m over log n plus and some constant, you're going to get the instance optimality term. You're going to get En of u square. You're going to get this epsilon u square that we saw before. And you're going to get something like, which is not so surprising, you're going to get n over m sigma square. I mean, that's the typical variance term that you find in any statistical estimation method. You cannot escape it. Okay? So then you retrieve the rate becomes not the approximation rate, it becomes the estimation rates. Okay, but if sigma goes to, okay, it also depends on the size of the variance of the noise. Okay, so actually it's interesting to compare this bound with the bound that you get on bounded regression in the non-active learning setting. When you don't choose, you get something. You get bound that you could compare to that. When you don't, when you sample according to an unknown density function, but then that imposes you the error first that imposes the L2 error in which you're going to measure. It will be the error with respect to the marginal, the L2 error with respect to the marginal distribution. And it's, you get something which is different, which is not as good, precisely because you don't choose, so you don't get to choose. So you lose something. Yeah. Okay.
If there are no further questions, thank you very much. Great block.